Welcome back, everyone. So what I want to talk about next are what we call the airbound formulas for our different approximation methods. We'll have one for the midpoint rule, trapezoidal rule, as well as Simpson's rule. Don't really cover them for the left endpoint and right endpoint rules. So what our airbound formulas allow us to do is, if we are making some approximation using the midpoint rule or the trapezoidal rule, that's what we're going to start with. Well, if we're making some approximation and we know our n value, we can determine an upper bound for our error. So we know our error won't be any more than this number that comes out of this formula here. What these formulas also allow us to do, and this is what I think is really, really cool, is we can kind of work backwards and say, well, if we need our approximation to have a certain degree of accuracy, like to 3 or 4 decimal places, or however you want to describe your accuracy, we can kind of reverse engineer or work backwards with this inequality and formula and find the value of n, the number of subintervals we need in an approximation to obtain or guarantee that desired amount of accuracy. There are a couple tricky things we have to watch out for when we are using these formulas or inequalities. So let's go ahead and see exactly what those tricky things are. So in this setup, we assume that the second derivative of the function in our integral is continuous on our interval of interest from a to b. This is the tricky part. There's going to be some number k such that the absolute value of our second derivative of our function is always less than or equal to this number k on our interval of interest. If that's the case, then the error in approximating our definite integral from a to b of our function f is going to satisfy one of these two inequalities depending on what type of approximation we are using. So this first one is the absolute error for the midpoint rule. So if we're using the midpoint rule with n subintervals, this is the error formula or airbound formula we would use. So it's saying the absolute value of our error is going to be less than or equal to that special number k times the quantity b minus a, which is the length of our interval, raised to the power of 3, divided by 24 times n squared. And remember, n is the number of subintervals we are using in our midpoint approximation. We aren't going to get into the details of deriving these error-bound formulas. That's something you'd probably do in like a numerical analysis class. But I can give us a little bit of insight into where these formulas are coming from. So this number k is related to the derivative and second derivative of our function. And remember, the derivatives tell us the rate of change of our function, and the second derivative, when we're not thinking about concavity, tells us how quickly the first derivative is changing. And so what we have to remember is that the derivative as well as the first derivative of our function are telling us about the rates of change of our function. And if we have this upper bound for the absolute value of a derivative, that's really saying, well, the rate of change of our function, whether it's the function or its derivative, is not going to change by any more than this number. So what we do in the analysis that we're going to skip is make an argument that, well, if we know that our first and second derivatives aren't really going to change by this much, then that means our functions can't change by so much either. And that's what these inequalities are kind of describing. What's like the most our function could be changing by. So once we have an idea of how much our function could possibly be changing by, we can then create these inequalities for the error, or how off is our function from what it should be. And the 3 approximating techniques that we focused on so far are the midpoint rule, the trapezoidal rule, as well as Simpson's rule. And we do have an airbound formula for Simpson's rule. It's just slightly different than these first two. I'm going to write that one up next. And so here we have our airbound formula for Simpson's rule. It has a lot of the same ingredients as our previous airbound formulas, but one of the big differences is what this number k is now representing. So in our first 2 airbound formulas, k was representing the upper bound, or this number that is bigger than or equal to the absolute value of the second derivative of our function on our interval of interest from a to b. Well, for our Simpson's rule airbound formula, we're still working with this number k. It's playing a very similar role, but now it's for the fourth derivative of our function instead of the second derivative of our function. So with that, we can say that the absolute value of the error when using Simpson's rule with n is going to always be less than or equal to the special number k times the quantity b minus a to the 5th divided by 180 times n to the 4th. We're going to use this airbound formula in the same way as we'll use the other ones. If we make an estimate or an approximation, we can kind of get an upper bound for what our error might be, or we can kind of work backwards, and this is how I prefer to use these formulas, to figure out the n value needed so that our approximation has a desired amount of accuracy. A couple of quick final observations before we start looking at some examples of finding k and using these airbound formulas is, well, for our midpoint and trapezoidal rule airbound formulas, everything's almost exactly the same. The only real difference is in this denominator we have a factor of 24, and in this denominator we have a factor of 12. So if everything is set up exactly the same, what we can see and what these airbound formulas are telling us basically is, well, this has a bigger denominator, so it's going to be a smaller number. The airbound formula, or the air using the midpoint rule, is going to be smaller in general than the air using the trapezoidal rule. We can't really make any comparisons between our Simpson's airbound formula and our other ones because k is playing a very different role. Remember, k is related to the fourth derivative here, while back to the second derivative here. The other thing we can notice with all these airbound formulas is that this quantity b minus a is like the length of our interval, and it's raised to these powers of 3 or 5, depending on which airbound formula we are using. So if the length of our interval, that quantity b minus a, is small in size, and here by small I mean less than 1, then when we raise it to a power of 3 or 5, when we raise a number that is less than 1 in absolute value to a power of 3 or 5, or any large number, it's just going to keep getting smaller and smaller. So this means if we're on a small interval, our approximations are going to be pretty good, while the other scenario is if our interval is larger than 1, then b minus a, or some number larger than 1 raised to powers like 3 and 5, are going to get bigger and bigger and cause our error to be bigger as well. So we can do a little bit of analysis here, and what we can see is if we're using these approximations on small intervals, then they're going to be pretty good approximations because our function won't be able to change a whole lot, while if we use larger intervals, that gives more room for our function to change and more room for error to creep in our approximations. Welcome back, everyone. Here we're going to look at an example of using one of our airbound formulas. Here we are asked to find the value of n needed so that our trapezoidal rule approximation is going to approximate the definite integral from 0 to pi of our sine function to be accurate within a 1/1000th of the true value. Again, this is not an integral where we actually need to approximate it since we can do it directly using antiderivatives, but it'll be a nice exercise to see how exactly we can use our airbound formulas. And so here I have our airbound formula for the trapezoidal rule written up. It says that the absolute value of the error in using the trapezoidal rule is always going to be less than or equal to the special number k times the length of the interval to the power of 3 divided by 12n squared. And what we have to remember about that special number k here is that k is greater than or equal to the absolute value of the second derivative of our function. It's the upper bound for the absolute value of that second derivative. And so what is our goal? Our goal is to make the error in the trapezoidal rule to be less than 1/1000th. And so what we know is, well, our error, or the absolute value of our error, is definitely going to be less than this quantity, k times b minus a to the power of 3 over 12n squared. And so the idea is if we can make this quantity less than 1/1000th, or 0.001, then that guarantees that the error in using the trapezoidal rule will also be less than this number 1/1000th. And so now what we have to do is figure out which value of n makes this inequality true so that our error is less than 1/1000th. So we're going to have to find all these pieces for this inequality in order to make any progress. So a and b are easy to find, right? A is 0, b is pi. The hard one to find here is going to be k, and then only after we find k will we be able to work towards finding n. So we said a is 0, b is pi, and now we have to find k. Well, to find k, we have to remember that k is this upper bound for the absolute value of the second derivative of our function. So the first thing we're going to have to do towards finding k is finding the second derivative of our function. So the function we are integrating is our sine function. And what we know how to find the derivatives of our sine function. The first derivative is going to be cosine of x, and the second derivative is then going to be negative sine of x. And now that we know the second derivative is negative sine of x, we can take the absolute value of that second derivative and we can cancel that negative sign out, and what we end up with is the absolute value of our sine of x function. And what we end up with is the absolute value of our sine function, and we're only interested in this on our interval from 0 to pi. And on the interval from 0 to pi, the absolute value of sine of x is the same as just our standard sine of x function. And so here is what the graph of our second derivative and absolute value would look like for this function. And remember, k is just the upper bound or the maximum value of the absolute value of our second derivative. And so we can see, or we can just remember that our sine function has a highest point at 1. So for this example, k is going to be equal to 1. In other examples, we might have to do a little bit more analysis, and it might be pretty difficult to find our k values. And so what I usually allow students to do to find k, whether it's using the midpoint, trapezoidal, or Simpson's rule formula, is just to use your calculator to help you find k. So you will want to still show your work for finding that second derivative, or the fourth if you're using the Simpson's rule. And then what you can do is just graph the absolute value of that second or fourth derivative on your calculator, and then use your calculator to help you locate that maximum. If you are using your calculator or computer to help you find this k value, it's going to be really important to remember to put your function in absolute value before you graph it. Otherwise, you might miss out. Another thing you can do to avoid having to work with the absolute value function on your calculator or in your computer is, well, if you don't work with the absolute value of the second derivative, but just the second derivative of the function, then what you have to do is compare the largest positive output on your interval of interest with the largest negative output on your interval of interest. Ignore the signs, and whichever one of those is bigger will be the k value you use. And I'm just making all this up here for the sake of explaining, but suppose we're working with some different function and this graph doesn't quite to scale, but maybe this is the graph of just the second derivative of our function and we haven't taken the absolute value of it. Well, the highest point would be at y equals 1, and the lowest point would be at negative 4. So if we did take the absolute value, that negative chunk would get made positive, and the maximum value would become positive 4. So our k value in this made up little side example would be positive 4 and not 1, right? We have to think about these largest positive and negative values when working with the second derivative outside of absolute values to help us find k. All right, but for our example, we now have a, b, and k, so we can plug all that into our inequality and now solve for n. All right, so let's plug everything in and see what we end up with. So we know our k value is 1. I'll write that down even though you don't need to write a factor of 1. b minus a is going to look like pi minus 0, that's raised to the power of 3, and then divided by 12n squared. And we want that to be less than 1/1000th. And I'm going to go ahead and just express this in its fraction form. And so if we clean this up a little bit, just simplify it, we get pi cubed over 12n squared is less than 1/1000. Now to make any progress from here, we have to be a little bit careful and remember some of those rules for working with and manipulating inequalities. Basically, it's the same as working with an equation, but if you reciprocate both sides of an inequality and the sign doesn't change, then you have to reverse the direction of your inequality. And if you multiply or divide your inequality by any negative numbers, that is also going to reverse the direction of your inequality. And so what we're going to have to do here is either think about cross-multiplying or reciprocating both sides of our inequality. Depending on how you view that, you should end up with 12n squared over pi cubed is going to be greater than 1000. All right, so our next step would be to try to get n by itself. So we can get n squared by itself by multiplying both sides by pi cubed. So that'll give us 1000 pi cubed. And then we have to divide both sides by 12. So now we know n squared is always going to be greater than this number. And now to get n by itself, we can just take the square root of each side. And we see that n has to be greater than the square root of 1000 pi cubed divided by 12, and that works out to be about 50.83. But remember, n has to be an integer here, so we're going to always round up. So we would set n to be equal to 51. So if we wanted to approximate our original definite integral from 0 to pi of our sine function and have our answer be accurate to within 3 decimal places or 1/1000th of a unit, well then we'd have to use at least 51 subintervals. Another little side note about all these error-bound formulas that I think I forgot to mention earlier was this number in this example of 51 guarantees that we're going to get that much accuracy. It is entirely possible that we could use a smaller n value and get the amount of accuracy we want, but by using this n value or any n value bigger than this, we guarantee that we will get that much accuracy. There is one other thing you're going to want to watch out for when finding these n values that won't be a big deal for our midpoint rule or our trapezoidal rule, but for our Simpson's rule, remember, n always has to be an even number. So if this was an example where we were using a Simpson's rule instead, and we ended up with n equals 50.83 or 51, rounding up to 51 wouldn't be enough because that's an odd number. We'd have to round all the way up to 52. So don't forget that for Simpson's rule, n has to be an even number. Welcome back, everyone. In this example, I want to revisit one of the earlier examples we did. So here we're going to estimate the error in using S6, our Simpson's rule approximation with n equals 6, to approximate the definite integral from 0 to 1 of the function e to the x squared. Remember, we used Simpson's rule to make this approximation in an earlier example. And the approximation we came up with for S sub 6 was about 1.4628734555. And now we want to know, well, is this accurate at all, or how off are we from the true value of this integral? This isn't a question we could answer earlier, but now that we've discussed our airbound formulas, we will be able to answer this question. And so the airbound formula we're going to need here is our special airbound formula for Simpson's rule that says the error in using Simpson's rule is always going to be less than or equal to that special number k times the length of our interval to the power of 5 divided by the quantity 180 times n to the power of 4, where n is the number of subintervals we are using in our original approximation. So in order to solve this problem, we have to figure out the values of k, b, a, and n. K is the most difficult one, and we'll save that for last. Let's get the easy ones out of the way. A and b are just the endpoints of our interval of interest. So a is going to be 0. B is going to be positive 1. In this case, we know what n is. N is going to be the number of subintervals we use in our approximation. And here we are told that that is 6. And so the last thing we have to find is k. And the way we do that is by going through that process of finding the fourth derivative of our function, considering the absolute value of that fourth derivative, and then what is the maximum of that absolute value of the fourth derivative on our interval of interest. Well, we know our starting function f of x is e to the x squared. Using our chain rule, we can find the first derivative of this function pretty quickly. It should end up being 2x times e to the power of x squared. Well, then we need the second derivative of our function. This is going to be a good little Calc 1 review. So to find the second derivative, we have to use the product rule. That'll end up looking like 2 times e to the x squared plus 4x squared times e to the power of x squared. Right? It's the derivative of the first times the second. The derivative of the first is where this factor of 2 comes from. The second is our e to the x squared. And then according to our product rule, we have to add to that the first function times the derivative of our second, but the derivative of our second is 2x times e to the x squared. So we get 2x times e to the x squared, which simplifies to this formula we have here. So it's going to get a little bit nasty, but that comes with the territory. So I'm going to skip over some of this work for the third and fourth derivative, but when we do find the third derivative and simplify it, this is what we end up with. We end up with the third derivative of e to the x squared being 12x times e to the x squared plus 8x cubed times e to the x squared. Well, now we just need one more. Remember, this is where our derivative notation switches up a little bit. So the fourth derivative of our function is going to be found, well, by taking the derivative of our third. So we're going to have to use the product rule with the chain rule 2 times, add all those terms together and simplify. And we end up seeing that our formula for the fourth derivative of our function of interest is going to be this quantity 12 plus 48x squared plus 16x to the fourth times e to the x squared. And so now we can use our fourth derivative to help us find our k value. Remember, technically we have to use the absolute value of our fourth derivative, but if we graph this thing or analyze it because of all the even quantities, what we can see is this function is positive everywhere, so that step of taking the absolute value actually isn't going to be necessary. And now we could find our maximum on our interval of interest using some of those techniques from Calculus 1, but we're going to save ourselves some time and effort here and just, if we graph our function instead, if we graph the absolute value of this fourth derivative, or in this case just the fourth derivative, and look at the graph on the interval from 0 to 1, what we can observe is that the maximum occurs at that right endpoint when x is equal to 1. And so by analyzing the graph of our fourth derivative, we can find our k value. It corresponds to the output of our fourth derivative at that far right endpoint when x is equal to 1. And if we plug x equals 1 into our formula right here, what we end up with is the number 76 times e. And now the worst of it is over. We have found that difficult piece, our k value. Now comes the fun part where we just plug everything into our formula. And so now plugging everything in, we can confidently say, using our Airbound formula for Simpson's rule, that our error in using Simpson's rule with 6 subintervals is going to be less than or equal to our k value of 76 times e multiplied by b minus a to the power of 5. That's going to be 1 minus 0 to the power of 5. We have to divide that by 180 times our n value of 6, which is raised to the power of 4. And so now our calculator can help us evaluate this. And assuming I didn't plug anything in incorrectly into my calculator, we find that our error in using Simpson's rule with this setup is going to be less than or equal to 0.0008855. And so this was the approximation we came up with in our earlier example in using Simpson's rule with n equals 6 to approximate our definite integral. And now that we've done this airbound analysis, we can know that our approximation is going to be pretty accurate, right? At least out to like 3 or so decimal places.